Hi, so this is a run through of the practice questions from the Forces section of Roy White's excellent GCSE physics book. Check this out if you haven't used it. It's an excellent text, it's got lots of great graphics and pictures and good explanations, lots of things about the prescribed practicals and stuff like that. This stuff comes from the practice questions for Forces, page 22. And this is questions 1 to 3. Question 1a. State Newton's second law of motion. 2 marks. So we know Newton's second law as F equals ma, but if you're going to describe it in words, you should really rearrange it for a. So a is obviously going to be equal to F over m. So F is on the top line, and that means we can say that the acceleration of an object is directly proportional to the applied force. M is on the bottom line, so we can say and inversely proportional to the mass of the object, and that's how you state Newton's second law. A plane accelerates from rest to a velocity of 50 meters per second in 25 seconds just before takeoff. Calculate its acceleration. So first thing to notice is that none of these things is a force or a mass, so this is not the equation we can use, the A equals F over m. But we do know rest, initial velocity, we do know a final velocity, and we do know how long that took. So initial velocity u equals 0, final velocity v is 50 meters per second, and the time is 25 seconds. So the acceleration is v minus u over t, the change in velocity over the time, and that's going to be 50 minus 0 over 25, which will give us 2 meters per second squared. Now it says some of the forces acting on the plane are shown in this diagram, figure 2.20. Use your answer to part B to find the mass of the plane. So what we've got here is some forces acting on the plane causing it to accelerate. You can see we've got a thrust of 60,000 newtons and a drag of 1500 newtons. So that's going to give us a resultant force where we find the difference between these two and see what's left over. So we can't use the whole 60,000 newtons, we have to take off the drag. So if I calculate a resultant taking to the right to be positive, then I can count the 60,000 newtons as a plus value and add it to a minus 1500 newtons to get the net forward thrust. So all I'm doing is adding all the forces together, but the plus here tells me that one points that way and the minus tells me that this one points that way, and I'm just adding them together and seeing what I get. And what I get is 58500, and it's positive, which means it points that way, which is good because that's where we want the plane to go. So if F equals ma, then m equals F over a, and that's going to be a resultant force divided by the acceleration we found in the first part, which is just 2. And that's going to be 29,250, and that's going to be in kilograms. Question 2. State Newton's first law of motion. 2 marks. The first law, remember, is the test of whether or not the forces on an object are balanced, and it states that if the forces are balanced, or if there is no resultant force, that the object will either sit still, remain at rest, or move in a straight line at a steady speed. So if there's no resultant force, it can't accelerate. So if it's sitting still, it has to just continue to do that, and if it is moving, it's not allowed to change speed or direction. A fighter plane of mass 3,000 kilograms lands on the deck of an aircraft carrier. An arrestor cable exerts a force of 90,000 newtons to oppose the motion of the plane. Let's just see what that looks like. Now it says the arrestor cable brings the fighter plane to a stop in 2 seconds, so we'll sort of come to that in a wee minute. Let's have a look at this, calculate the acceleration. Here we do have a mass, and this is what you always do. Stop and write down what they've told you. They're clearly telling us a mass up here, and they're telling us a force. So this is a straight version of using Newton's second law, F equals ma. And the acceleration is going to be F over m, which is going to be 90,000 newtons over 3,000 kilograms, which is going to be 30 meters per second squared. So we're saying now that the acceleration that the deceleration that the cable produces brings this thing to rest in 2 seconds. Calculate the velocity with which the fighter plane landed on the deck of the aircraft. Okay, so we've got an initial velocity, 2 seconds worth of deceleration, and a final velocity of 0. So we start making out a UVAS list. We don't know U, we know the final velocity is 0, we know that A is going to be minus 30 meters per second because it's points the opposite way to the incoming velocity. We don't know how far it goes, and we do know that the time is 2 seconds. Right, so we know that A is V minus U over T, multiplied by T, and we get AT equals V minus U. Now, I don't want to leave minus U here because that will be extra confusing. So if we add U to both sides and subtract AT from both sides, we should get it the way around that we want it. Yep, so I have added a U to both sides to get this U over here, and I've subtracted AT from both sides, and we end up with minus AT there. And we can fill this in now. So V was nothing, A is minus 30, so we've got minus 30 times 2. So U must have been 60 meters per second. Question 3a, describe an experiment to verify Newton's second law of motion, and that's worth 6 marks, so that's obviously going to be second law is F equals ma, so you're looking at the relationship between acceleration and force and acceleration and mass. So the standard experiment for this is this system with the trolley and the pulley and the weights. The weights provide a downward force. That force gets transferred to here, and you can investigate then how much force causes how much acceleration of the trolley. You can also keep the force constant and add loads to the trolley to change its mass and see how a constant force with a changing mass affects the acceleration. So you might describe tilting this runway to friction compensate it. Then you would describe how you could be adding discs here with one individual 1 Newton discs giving you a total pull force. So single Newton on its own, see what acceleration you get. You would also need to figure out how you're going to get the acceleration, so you might need to explain how you would introduce light gates and an interrupt card. So this is a double interrupt card. The easiest way to get acceleration is to use a double interrupt card. So you've got the trolley just here. You've got a single light gate, your pulley system, and the idea is that a double interrupt card and a single light gate can give you accelerations. So you set the system up with a fixed trolley and a set of different forces that you're applying, and then you measure some accelerations using the light gate and dial logger. Then you go again with a set of masses of the trolley and a set of accelerations for a fixed force. So this time you don't change the pulling force, you just change the mass of the trolley by adding masses to the trolley. So for example, you could add 200 grams and that would give you a trolley that maybe starts off with 1 kilogram, then 1.2, 1.4, 1.6, 1.8 and 2.0, and you keep this value here of the force fixed, so you don't change the masses that are pulling it, you just change the mass of the trolley itself. And so in both cases where you're changing the force, you get a set of accelerations. Where you change the mass, you get a set of accelerations, and they're all coming in via this light gate and data logger. So if you plot a graph of acceleration versus force, it will be a straight line increasing, and a graph of acceleration versus mass will be a curve like this, but acceleration versus 1 over mass will show that it's proportional to 1 over mass. So the 6 marks will be for valid points of what you're doing. So there'll be some marks for the setup, some marks for what you do, and some marks for what you do with the results, like plotting the graphs. Second part of the question then shows you one of these acceleration versus force graphs, like the one we drew first here. Use the graph to calculate the mass of the car. Okay, so we have some accelerations for some various forces, and you can see here at the top of the graph that we're getting an acceleration of 3 when the force value is 4,500. So we've got an acceleration of 3 meters per second squared when the force was 4,500 newtons, and we know that F equals ma, so m is going to be F over a. So that's going to be 4,500 over 3, which is going to be 1,500 kilograms. So part C then says, on a different journey, the velocity of the car increased from 6 meters per second to 18 meters per second in a time interval of 4 seconds. Calculate the acceleration of the car. So that's just a straight u-vast, with a is v minus u over t. So if we just make ourselves a bit of space here, we can make out our u-vast list. U is 6 meters per second, v is 18 meters per second. A is what we're trying to find, S is unknown, and t equals 4 seconds. So A is v minus u over t, change in velocity over time taken, and just fill that in now. So 18 minus 6 is 12, and 12 over 4 is going to be 3. So A is 3 meters per second squared. Okay.